The structure for today, the first hour will be going over some stuff which you already talked about and just like completing this beautiful picture of representations of Sn by its like branching rule, this Modular approach. And then afterwards we just have a bit of a discussion, general questions or things you want to talk about. Great. And so because the first half I am just sort of trying to go over some things, it's sort of like I think there's a beautiful picture here to be like, and it's really important to try and just like grasp the picture, even if certain aspects of it you don't remember. I find it's a really, really nice picture to have in your head as like an organizing principle of representations of Sn. So like it's okay if we don't go over the proofs or like do more examples, because I really want to just try and instill this perspective on Sn, because I think it's really, really good. Okay, so I'll start off with just reminding us about some things. Oh, and so if you have any questions, please ask. Like, no point you're just sitting there not getting in out of it. So we have this special commutative subalgebra sitting inside CSN, and it's got these generators. X1, n minus 1. And these generators are xi, the sum of, you remember, so I think it's j I as this goes over j.
Is the loss of x n rather than n minus 1?
Yes. Yeah, you're right. So let me just double check these are in fact
I think it's right.
The generators that I think they are. Yeah. So j equals 1 up to this one. So let's just write this out. 1i plus 2i plus 3i plus I minus 1 I. And we can also, okay, you could write this in terms of the cost of the generators, but I think this is a better way. Okay, so we've got this large commutative subalgebra sitting inside CFSN. And the point is that, like, once you know that this large commutative subalgebra is floating around, it's really, really helpful. So I'm going to draw the diagram of this board that I can't erase. It's really, it's a really good diagram. So this is just the diagram for partitions. Sorry, I'm just trying to figure out how to turn on the lights better if it's not working. Oh, that's the worst of all. There we go.
Oh,
okay.
There you go.
The last one. That's always the one. So in general, I would say like, this, as far as combinatorial objects go, this is like one of the richest combinatorial objects that we have. It's just the best. So I'll draw a little bit more just for fun. Okay, and so the way we're thinking about it is that you can either start from scratch, or you can start knowing what the representations of Sn ought to look like. And we can sort of take both approaches. Like you can pretend you've never seen them before, but it's more helpful if you have seen them before, because then you sort of know what you're working towards. And so the easiest thing that we're working towards is to say the irreps are indexed by partitions. We're the irreps of Sn. So, right, so this is irreps of S1, this is irreps of S2, this is irreps of S3. Okay. And then if you're given an irrep, say, of S4, then you restrict it to S3, it splits as a sum of this plus this. And it splits with this multiplicity 1 property. And so then you say, okay, well, then you go down one further, it splits again, and so this gives any irrep of Sn a canonical sum into one-dimensional subspaces given by indexed by paths down from this index point down to the base partition. Okay, and so this is like any irrep of Sn naturally has a bunch, like a canonical sort of basis of lines. So basis that's not well defined up to scalar, but just spanning lines sitting inside. Okay, and this algebra, basically, the knowledge of this algebra sitting inside the group algebra of Sn is equivalent to having this basis of lines, or this basis indexed by paths, because those paths are exactly the eigenspaces for this algebra. Yeah. So, in this, if you had this picture and you knew this multiplicity one branching rule, that would give you a bunch of one-dimensional subspaces. And you could, define the algebra abstractly as the thing which preserves all of those eigenspaces, those one-dimensional subspaces. And this is just a concrete way to write down what that algebra actually is. Okay? So, yeah, so this is sort of what we got to last time. We've got this beautiful branching rule. We've got this lovely algebra which sort of picks out our eigenspaces. But now we want to say, like, okay, great, we've got PZN acting on any irrep associated to a partition. It will break up into one-dimensional subspaces. Each of those one-dimensional subspaces will have a character, like, will just be a one-dimensional representation of this commutative algebra. And we have canonical generators of this algebra. So, like, what this tells us that each of those lines just gives us a sequence of numbers. Okay, so write that down. So V lambda has a basis indexed by Tableau. So these were the Tableau slash paths, which we can call lambda equals sum of T, C, dt, and gzn dot dt equals cdt. So each one is fixed by this whole algebra. And now, because we have this nice choice of generators, we can say that each xi acting on bt will be just some number, that maybe I'll call it ti for now, times bt. And the whole we didn't quite get to last time was sort of what are these numbers? We sort of saw at the end. So this is in the sense in, like, you have all this nice abstract one-dimensional subspaces, you have this nice abstract algebra floating around, but this algebra has generators. You actually want to know what the numbers are. Like, what actually are these things that are indexing? So this is what could be described as describing the spectrum of this with respect to these generators. Okay.
Because maybe TI is not the best notation. I don't know if you're going to continue using it.
No.
There should be a T should be in this, like in the subscript as well. Because it depends on T.
T should be in the,
like, it depends on T and I. That number. So if it was for like
Just call it CI, like
contact data by.
Yeah. Okay. Okay. Does anybody have any questions about sort of the setup or where we're about to try and go? It's like, we've got this lovely abstract framework, and now we're just going to try and make it more concrete, more combinatorial. Okay. Great. So let's we can rephrase this as take a tableau, associate this alpha t equals 1, 2, alpha n, Cn, the eigenvalues of xi on bt. Okay. So I think Jordy started sketching this. We'll continue. So basically, I'm going to tell you the answer, and then we'll just try and unpack it, see why it's true, get it to a point where we understand it a bit more. So this is the like content of a tableau. So to this example, I have a tableau. 1, 2, 3, 4.
It's probably a bad convention. I would start with 0. Oh, this is tableau. Sorry, yes.
Yeah. Okay, so we want to compute the content. So then we do this like, I don't even know if this is the standard way of doing probably. So this is the way I've been thinking about it. You know, your contents live on a grid. 1, 1, 1, 3. That's 2. 1, that's 2, minus 3. And then, so given a tableau, to read its content, just say, okay, well, 1 is 0. And then 2 is 1, has content 1. 3 has content 2. So this is more of just a memory device. That's all. Okay, 4 minus 1, and then minus 2, minus 3, and then 0. So this is our content vector. In particular, it's just some vector in Cn, and the claim is that these content vectors are exactly what we're after. Okay, so that's the content of the tableau. Content of the tableau, or thinking about it as a path, this is the content of the path.
So if I know the content, I can go back to it.
Yes, yes. And so how might we do that, right? Like, because I think this is an interesting point that, like, when you think of a partition, you draw it and you say, great, I know what a partition is. But then if someone just like gives you a list of numbers, it's like, okay, it's not too hard to get from the list of the numbers to the drawing. If someone hands you a list of numbers and says, this is a partition, and then says, all right, what's the list of numbers associated to the transpose? You have to do a little bit of work to think about, you know, how to do that. So I would say that, like, representing the same data becomes very non-trivial in this picture. And so this is like, you know, this is the sort of geometric or even paths is one way to represent the data of your tableau. And then this is another way to represent that data. And this content vector is another way to represent that data. And all of these are quite different, right? So for instance, let's just see how to get from this amount of this bit of data to this bit of data, right? So, and I claim that the way to like understand this and to actually prove things is to realize that something is like a valid content on n letters if it is also a valid content on n minus 1 letters. In other words, you want to use induction. So, but anyway, so let's just see. Say we've got this one. We've got n things, and we can see like how many zeros are there. There's 2 zeros. How many ones are there? There's a single 1. And there's a single 2, a single minus 2, and a single minus 3. Which means that along this diagonal, we have 2. Along this diagonal, we have 1. Along this diagonal, we have 1 thing. Along this diagonal, we should have 1. This diagonal, we have 1. Along this diagonal, we should have 1. And so counting up the multiplicities of each of these things gives you the like number of parts of your partition in each of these diagonals. And you see that if you have these numbers, they are exactly like they faithfully give rise to a partition. And then once you have the shape of the partition, then you just need to say, well, okay, I remove the 0 point, and there's like a unique way to do that once you get the shape. So maybe I'll write that down. So the claim is that the shape of the tableau, which is like the shape of the underlying partition, is given by the multiplicities of the values in the content. Content along the diagonals. So this is, I'm not quite sure the best way to phrase this, but like, so this is sort of yet another way of describing a partition, right? Like you could describe it as a picture. You could describe it as a list of numbers. You can also describe it using a different list of numbers if you give the diagonal, like the diagonal values. And those will all be sort of faithful ways to describe a partition, but it's not necessarily clear how these ways interact, or like, you know, which lists of numbers give you valid partitions when you look in the diagram. It's not obvious. Or it's like, it's not obvious. So yeah, so this is like the content, that's one way, so that's how we recover the partition. You count the multiplicities, put them in diagonals, and you see there's a partition, and then because you've got this list, you see which boxes to remove to get your path out. Okay. And so then, yeah, so the theorem is that the spectrum, as in this subset, N, is exactly on N content vectors of partitions. Content vectors of tableau, maybe I should say.
And a tableau if you want to be picky.
Okay, yeah. So don't know enough to know exotic
Exactly.
types of tableau. Well, I know that there are exotic. Maybe I should be. Okay, so yeah, so this is sort of the way to understand this is like this spectral perspective sees young tableau, or you know, gives you a basis indexed by paths, and spectral perspective gives you numbers. It's the number you get associated to a tableau, it's the content sequence. Great. So, I mean, it would be nice if we could say, you know, what sequences show up here, like sort of intrinsically. Like, you know, how can we characterize these numbers without just saying is the content of a tableau? And there is a relatively simple combinatorial rule for this. So, but actually, but maybe I won't do that yet. I'll so yeah, that's one thing which we should do, which is, you know, understand these content, or understand the spectrum, understand these lists of numbers that you actually get. But I would say possibly more important is a beautiful fact about the action. Okay? So the idea is, you know, we've got this basis of paths. So maybe I'll give an actual thing. So like say it's here, 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 it's here. And our generators of our symmetric group, we've got, you know, S1 up to Sn-1. And the claim is that, so the claim is that Si only affects the ith partition of.
Hey John, how are you? Hi, nice to meet you.
All right. So this is saying Si applied to this basis vector is equal to you know, alpha t plus t prime for some alpha beta where t prime has so lambda and my notation is going to crap here. So has the same path, I'll just say has the same path except for at the ith vertex, has the same path aside the ith set. So for instance, say we were in here and we have a path that goes from here to here. Okay? Then if we, and so this is in S5. So the claim is that if we hit this path with S, okay, yeah. So then the claim is, you know, if you hit this path with S4, then like the little generator S4, you're only going to be messing with this part of it. So in other words, you're going to start here, you're going to end here, and you're maybe going to mess with this. Now, in this case, there's only one path from here to here to here, so you can't mess with it at all. However, if we started with this path, say, and then we applied our fourth Cox as a generator, we could get a linear combination of this path and this path. So we're only moving at this step. Or, you know, start at this path, and then you apply S1. Well, you'll get a linear combination of this thing and this thing. So it's sort of, and like, it doesn't necessarily just permute these things. Like when I say there's a linear combination, these alpha and beta should be different. But this should be thought of as like a locality thing, right? Like when you act on this path basis, you don't just permute the path basis, but like you're pretty close, right? Like you're only messing with a basis vector by a different basis vector, and it's combinatorially very well. There's a clear combinatorial way to figure that out. So yeah, so, I feel like a lot of these things.
Maybe you're going to say it. The other way of saying it is, if you instead of giving me the path, you gave me the tableau. It's like saying you have that standard tableau plus the standard tableau you get by switching the I and I plus first labels, if that's still a standard tableau.
Yes. Yeah. So it's sort of like saying, you know, if you just had these, you want Sn to act by permuting labels. But that doesn't give you valid things in this set. But if it does give you a valid thing in this set, then like it only depends on those two things. Right. Okay, so yes, I would say like just to sort of thinking about these, how would we actually prove this? And so can anyone think how might you prove a statement like this? So the claim is that to prove this, is that it suffices to show that when you hit, so if you take one of these basis vectors and you hit it with Si, and you hit it then with the group algebra of Sj, that this representation is isomorphic to J. Say lambda J. If T is lambda 1, lambda 2, lambda J. Lambda N. So if T is our sequence of partitions or a path in the branching diagram, then we can act on it by SI, and then we act on it with SJ. The claim is that it suffices to show that we have this isomorphism when J does not equal I.
Do you mean like the partition lambda1 dot dot lambda j?
Lambda1.
You're v sub lambda j. I don't know what that means.
So this is the irrep of SJ indexed by the partition lambda j.
Lambda j is not a partition as you currently written. Do you mean lambda1 up to lambda j?
Yeah.
Lambda is just a number. I think you mean like the partition.
You mean the truncated partition.
Truncated one?
So I think maybe I'll.
Maybe I'm confused.
So lambda partitions. So that means if I have a sequence of this is saying I have a sequence of partitions, aka
oh, it's
a walk up
partition.
the graph. And so yeah, it is like
I see.
Yeah. I sort of don't know a nice way to do this.
I get it, yeah.
I would say it's better in the notes, but it's still not best. I don't know how it's like.
All right.
Yeah. Okay, yeah. So the claim is it suffices to show this. Right? So why is this? Well, if we take this T and restrict it to SJ, okay, so let's split it into two cases. Right? So if J was greater than I, this would be saying that our tableau, say it lies here, and our SJ lies up here. Well, then when we hit it with this, so we're living in S5, and we have, and we want to look at, say, the fourth generator, and then we want to know what it does to this path. So if we apply that fourth generator to VT and then hit it with S5, that's the same thing as what we started with. So let's breaking this into cases. J is greater than I, then when you hit this with this, it's J psi dot VT equals C SJ T, which is just V lambda J. Okay. And then if J is less than I, then SI commutes with C of SJ. So in particular, we could swap them around and we would get that the representation of SJ is just what we would get by acting on VT. It's SJ. So what's the? It's really it. But okay. So I claim that both of these cases are easy for different reasons. But what I'm still not completely convinced by is why it's enough to show this claim. So I was convinced about this before, but now I'm sus. So like.
You also need that like if you have I equals to J, then there's only like two Fourier representations that can appear somehow. Because I mean you only have two tableaux showing up in this SI.VT. And I guess it's not obvious to me why you only have two terms there. Okay, maybe that's something that's possible, but not obvious to me.
Yeah. So I think because like, and I'm wondering whether that's implied by the combinatorics, because it's like if you've got two paths which are the same and differ only at one spot, one can check in this branching graph. There's only two possible things you can have.
Okay.
So this would be the statement that like in this post set, any rank 2 interval has at most two things in between it, and like the interval from here to here has 2, the interval from here to here has 1, and that's it. But so this locality is like a very, very, very nice thing. And so I think it's really worth understanding. And I feel very silly that I can't remember how it goes.
Well, they're only diamonds because we're adding
just this
two boxes, so that at most 2 ways to add 2 boxes. That's why they're only diamonds.
Yeah. But like, why? So, but why is the action on, like, if I want to claim that it only messes with, like, it doesn't mess with any of these other spots? Oh, okay, yeah, okay, yeah, all right, okay.
But that's exactly what you want.
Yeah.
Outside, it's fixed, and you only have a diamond in the spot I equals J.
Yeah. So like, because if you restrict your group and then you act on one of these special vectors on the representation, you get the irrep according to the truncated path. So you want to say that that doesn't change.
That's right.
When J is less than I, and when J is greater than I,
it doesn't change.
It also doesn't change.
That's right.
From the top. Okay, yeah. Okay, great. And so then, once we're happy with this reduction step, both of these steps aren't very tricky to show. The only one is that this one is saying that if it commutes with this, then it's like saying, well, if you could just move this out here, then this would be taking the representation, you would take the representation of Sj applied to Vt, which gives you that, and then you would just be hitting it with something that commutes with this, and this is a general property. Whenever you have a submodule and you hit it with an endomorphism which commutes with it, you'll get a new submodule, and those submodules will be isomorphic. You hit it with an invertible element that commutes with it. Okay, great. Okay, so now I want to talk about content a little bit. Mainly, how can one recognize these? Because, and I would say that like, an answer to this problem is sort of saying like, how can you interpret a partition when all you're allowed to do is add boxes and you know what diagonal they sit on? This is just a very weird way of encoding, or weird to me, way of encoding a partition. And so understanding which possible content vectors show up is exactly formalizing those sequences of numbers which are valid. Okay, so I'm not sure if I want to actually prove it, or maybe I'll just state, okay, the claim is the n is those alpha 1, alpha 2, alpha n with 1. Alpha 1 equals 0. And so as I'm writing these, let's check why they're true for partitions, right? Like, this is, so why must the first thing in a young tableau be 0? Well, it says that if you start, the first box you add to get from the empty partition needs to be on the diagonal, which has content 0. Right. 2. For all q greater than 1, set +1. Empty. Okay, so this is saying that whenever alpha q, like at the qth step, either plus or minus it must have come before. Okay, so why does this make sense in partitions? Well, if you are adding a box that lives in this diagonal, then at some point, or in any diagonal, then at some point you'll have needed to have a box which is, before or after it, as in here or here. Like say, if you're adding this box, you needed to have added this box to this one at some point before in your process. Okay. And then finally, you is A, Q. A plus 1, A minus 1. In its set. So this last condition is saying if we have two content things which are the same, right? Same value, then plus or minus both of those must have occurred between them. Okay, so why is this true? Like thinking about partitions, this is saying that if we add two boxes like on the same diagonal, and we're adding them one at a time, then at some point we must have added some things between them. Yeah, so and that's it. So the claim is that, like, okay, these are satisfied for all partitions or for all standard Tableau. And then the claim is this exactly characterizes those sequences which come from standard Tableau. Okay? And so to prove this, one basically needs to check, or sort of use induction. You assume that it's true for n-1, and you see what can happen if you want to add an extra box. Right? So let's say we wanted to add an extra box. Say we wanted to add it on this partition. Well, and we are claiming that these rules, if these rules are satisfied, then we can in fact add that extra box. Okay? So let's say we wanted to add the box here. This one vacuous, that's our inductive step. This would be saying that if we want to add a box somewhere, we will have needed to add a box, somewhere here, like one next to it. So this one can be thought of as you need to place your new box adjacent to a box that already exists. Okay? And then this one is saying that, okay, if you place your box somewhere where there's already a diagonal, already something else on the diagonal, then you need to have something here and here. You need to have things next to it. And now we can think, okay, if you're trying to add boxes to a partition, what's going to stop you? Well, you're adding boxes that are, this condition says you have to add it next to something which you already had. And then, could you add a box here? No, because you don't have something here. So this is like basically sitting down with these rules and induction. It's basically how you prove that this exactly captures what you need to add boxes to partitions diagonally. Okay. So now I'll talk a little bit about the degenerate affine Hecke algebra. So the claim is like, if we want to understand the branching rule and we want to restrict it here to here, multiplicity free, surprisingly, that's not actually the easiest way to like prove this set of statements. And especially to prove that like this is the spectrum of this GZ algebra, like that requires some work. At the moment, we haven't put in the work to show that. We've just characterized the spectrum. I've told you that that spectrum is in fact what we expect it to be. It seems natural that it might be, but like to actually do it, you need to do some work. And so the idea could be, well, take a partition, restrict it here, and then look at the like effect of adding a box, and express this using this GV algebra. And unfortunately, this doesn't really work. There's not really a clear way to do this. But what does work, which is kind of crazy to me, is that if you restrict 2 steps, it just works immediately. That is exactly the right thing to do. You get a description in terms of your original algebra, which doesn't work for 1 step, and you just have to consider 1 and 2 dimensional representations, but it just all works. So here's the dilemma. So I'll say recall that on SK new where these are irreps is a irreducible DCSM CSK. Right? So like when you restrict something and you look at the Homs from your smaller thing, this thing has an action of this centralized algebra, also known as the Hecke algebra, and this will be an irreducible module. This is sort of not helpful if you can't recognize this algebra. And so this is the problem of what I was saying, when n equals 1, you can't, or at least you can't recognize the algebra and relate it to the GZ algebra, which is what we're trying to use to index everything. We're trying to understand it. So if when k is n minus 1, you can't, but, so consider S n plus 2 Sn. And honestly, this is kind of insane to me. Like, I would never do this. I would never see that it doesn't work for 1 and say, does it work for 2? That's crazy. So I'm just like, yeah, I think this is very, very clever. No, I've never thought of it. So the claim is that this equals center C S n plus 2 and S n plus 1. Right, so the claim is that when you restrict this, you get the center of the group algebra of a smaller thing, and it's generated by that thing, which you should think of as understood by induction, and then your 2 new generators, and then your Coxeter generator. And so, like, these things are all really, really natural from our picture, right? Like this Sn plus 1 and these 2 things. And in fact, Sn plus 1 sort of acts on the space of these 2 things. So the whole upshot of this is that, like, this relative step, when you take index 2, is all controlled by, like, the same algebra. You sort of start with something of here, and then you have an action of this extra little algebra, and that's what sort of tells you how things decompose. So, okay, so I'll just tell you the relations. So we set y1 equals xn plus 1, y2 equals xn plus 2, and s equals sn plus 1. Then one can check that s y2 equals y1s plus 1. Okay, and so this is exactly the relations for H2, which is the degenerate affine Hecke algebra. I think for the Coxeter group with a single transposition. So a very simple thing, in the sense that, like, what is this algebra? You've got y1, you've got y2, and you've got s. They satisfy this, and s squares to 1, and y1 and y2 commute. And that's it. Like, there's nothing else going on. So in particular, one can completely classify the irreducible modules for this algebra. Okay, so in this picture, if we do this step, we should get an irreducible module for this. And in fact, we can check that we'll get an irreducible module for this little piece. So it's all sort of controlled by this little piece. Okay, maybe I'll just describe what these modules are, prove it. But this is really sort of now a very small concrete problem, right? You've got, we want to classify the irreducible modules over this algebra H2. Because we know that those are what's going to show up.
So are those all the relations?
I mean,
that one, that the commute and s squared is 1?
Yeah, I think so. Yeah, there's nothing else. Okay, so let's classify the irreducibles. So y1, y2, s, and then our relation is s y2 equals y1 s plus 1. Okay. What are its irreducible representations? Well, especially in our case, we know that these two things will act linearly.
Chris, I just had a silly question.
Mhm.
So that's not actually the algebra though. I mean,
Well,
it's the center of Sn adjoin H2, right? Like
Yes.
you're adjoining these extra layers. So
Yeah. Yeah, okay, yeah. So I sort of swept something under the rug, which is that a priori it's just going to be a irreducible representation of this guy. And then my claim is that this irreducible representation of this guy is an irreducible representation of this when you restrict it. And you know, if we think inductively, like we can understand what this is by our sort of branching rule or by content, and like you restrict your representation and then tell you what you get in this part. The new information is the parts, the eigenvalue of this guy and this guy. That's sort of what you lost. And that's controlled entirely by this little heck algebra.
Was the center of Sn should just be acting by a scalar on that thing, right? Or maybe I'm confused, but semi has to act semi-simply, and so it shouldn't have to act by a scalar, and so then if it's the irreducible representation over the whole thing, then
Yeah, that's a good way to, yeah. Oh, right, yeah, of course, because like in this instance, the center of SK acts on this guy just by a scalar, and that's where this action comes from. Okay, yeah, so it's like this thing acts by just like a well understood scalar by induction, and these are the content that we forgot, or the parts of the spectrum that we can't see when we restrict. So that's what we're doing. Okay. So there's two cases. So because y1 and y2 commute, there exists a v simultaneous eigenvector for y1 and y2. So that means we just have y1v is ab, y2v bd.
So, sorry, you're starting with an irreducible representation of this algebra, or you just said there exists a v. So I just want to know your
Start with v and irrep of h2. So there exists a v in v, which is simultaneous eigenvector for these two things, because it's a commutative subalgebra. And then we split into two cases. So then two cases, which is v, SV, linearly independent, or v equals plus minus SV. Right, because S is a transposition, so it squares the identity, so it's going to act by multiplication by 1 or minus 1 if these things are linearly dependent. So maybe let's just handle the second case first because it's not too tricky. So if we know that this is the case, then where's our relation? There it is. So hit both sides by y1. You get y1v equals plus minus y1 SV, which equals plus minus sy2 minus 1v, which equals plus minus SVV minus v, which equals, okay, this plus minus and this plus minus cancel out, which is just BV minus plus V. Okay, so in particular, so A, the eigenvalue of y1 is equal to B minus plus 1 in this case. Right, so that tells us that like, and you know, this is sort of what we want, in that we want these things to start looking like content vectors, and the last two content vectors well, the fact that they have to differ by one is exactly what arises in some setups of partitions. Okay, so, and then the more interesting case is when they're linearly independent, and then we can check that, yeah, so on the basis of the SV, Y1 acts via the following matrix. Y2 acts by this thing. And so then, and then S acts by this thing. Okay, then great. Great. So this is the linearly independent case. And this is the linearly dependent case. And so in both cases, and then we can check that in this one, A does not equal B, and A does not equal B plus or minus 1. I think these are implied by stating this is an irreducible representation. Yeah, right, because like for this, at this point, we've got actual matrices. You can just check for it to be irreducible. That's going to force some conditions on these two things. So, and then the other case is that they differ by exactly 1. And so the way one should think about this is if you have like a path, you have a content vector, and you restrict it down here, down 2 steps. There are sort of 2 ways in which you can fill it in. Or there's 2 ways, or there's 1 way. And if there's only 1 way, you land in this setup, where you've sort of only got 1 degree of freedom, and your S just acts by plus or minus. And if there's 2 ways, it sort of switches between them according to this. So this would be another way of seeing the like locality at this top step. Is saying that it just messes with the top 2 paths, and it messes with them in a very controllable way. So yeah, this is sort of the start of the picture, but like, I guess the thing that I would want you to get out of this is like, this branching rule is amazing, but also that once you have this description, this whole picture just becomes, analyze this little algebra, and it will tell you everything, right? Because if you imagine doing this, and you imagine doing this for Sn plus 1, and then that should tell you what this Xn plus 1 should be, then this is like, if you're in that first stage that says Xn plus 1 determines Xn plus 2, if those eigenvalues determine each other, and, you can sort of bootstrap and build it up from there. But yeah, it's really sort of like the thing that you need to make this branching rule explicit and self-contained, and like describing the spectrum intrinsically is yeah, you need this H2, and you just need to understand its errors, which are 1 or 2 dimensional. So like, not spooky.
So did this prove that this statement that you're locally in the path, there's only, you choose 2 partition, there's at most 2 paths between them? Because that would be giving you
wait, as in the combinatorial statement that there's at most 2 paths?
Yeah,
does the locality statement? Because I claim the combinatorial statement is very easy.
Right.
This may give another proof for it.
I mean, yeah, doesn't it say exactly that? I mean, the dimension of that Hom space is the number of such paths. Is that correct?
Yeah.
And so the fact that it's irreducible, the fact that it's not.
Yeah,
that's correct.
Yeah. But the easy way to see that any rank 2 interval can have only 2 or 1 It's just that you're removing a box.
Right, but I guess if you were coming from the perspective that you didn't totally understand the branching rule and you were just like,
oh, okay, yeah. This
I
algebra would tell you that your branching rule is either 1 or 2,
yeah,
and it's determined by content.
yeah.
So then, like, you could pretend you just live on this side of things. You've never drawn a box in your life.
Yeah. Well,
it would be a sad existence if you were just dealing with these the whole time. But like, yeah. I mean,
but I mean, the branching rule is not obvious. I mean, right? I mean,
the branching rule from this perspective, or just at all.
I mean, to me, it's not obvious at all, right? The fact that if you branch from S and Sn minus 1, it corresponds to removing some box in the partition, like that. We haven't proven that. Have we proven that?
No. I would say no. Like, it's sort of using this, relating it to content, and then you prove it.
Yeah. So I guess I'm saying this seems like the first, maybe like, I don't know. To me, it's just helpful to.
Yeah. Because I feel like you possibly can, like, if all you're trying to get to is the branching rule, there might be sort of like ways of being much more efficient.
Yeah, sure.
But because we're sort of trying to see the whole picture, and even haven't really been proving anything properly. It's just been like, see the picture, see how it works. But yeah, and so one historical remark that I find really interesting is that I'm pretty sure Young's original description of the irreps of Sn worked with Tableau. So he said, okay, we've got a base of the Tableau, and then he basically wrote down local rules. And when you do that, you can check that you can fix your scalars in such a way that it gives a representation of Sn. So like, if someone just handed you this sort of rule for how do you mess with the paths, or how do you mess with the Tableau, you can do it, and you just check. Do a calculation, and you check the satisfies the break relations, and that was actually, I don't know if that was the original way. It was probably not the original way, but like that's sort of a one-step way to get at the representations method, which is already a little bit different to the one in the accounts, for instance, which is a different one-step method of getting the representations method. And this is sort of the complete opposite of a one-step.